Here we want to find the value of R, which is some sort of load that enables the circuit shown to deliver maximum power across these terminals A and B. So again, R is acting like the load. We have some supply circuit here, and we want maximum power transfer from our supply circuit to our load. In order to accomplish that, we need to find a Thevenin equivalent circuit for our supply circuit, and then we know that the load resistance that we need in order to have maximum power transfer is going to equal the Thevenin equivalent resistance for our Thevenin circuit. So our first step here is to find the Thevenin circuit. What that means in practice is for us to find the open circuit voltage of that supply circuit, the short circuit current of the supply circuit, and then the Thevenin equivalent resistance of the circuit. We'll find the three of those so that we have the Thevenin equivalent circuit, and once we have that, we can find the power being transferred to our load. So the first thing we'll do is find the open circuit voltage. We'll do that by analyzing this circuit with no load connected across A and B, but with an open circuit here. We want to find the open circuit voltage, VOC. If we can find the voltage at this node, and we pick our ground to be down at the very bottom, then the voltage at this node compared to the ground is going to be our open circuit voltage. So that's what we're going to look for. We also want to put the reference at the ground so that we'll have 20 volts here, and we'll have 100 volts there because we have voltage sources specifically connected there. If this is 20 volts and I go up another V phi, then this voltage here is going to be 20 plus V phi. If I'm at 0 here, I go up 100, I'm at 100 volts now, I go up this source, which is set to be V phi as well, then my voltage here is going to be the 100 plus V phi. And then I want to look at the currents that I have flowing. I'm going to have a current flowing this way, and a current flowing that way, this way, and that way. And so right now I have two unknowns. I don't know what V phi is. I don't know what this V is either. So I'm going to need two equations to solve those two unknowns. My two equations will be a node equation right here and a node equation right there. Those are the only two independent nodes that I have. Everything else is connected by voltage sources, and so those are all referenced to ground, so we have values for all of those. So I'm going to write node equations for this node and then for that node. So here I have my two equations. I have I1 flowing in and I3 flowing out, so those two currents must equal each other. Here I have I2 and I3 flowing in. Together they must equal I4 flowing out. I know the voltage across that resistor is V phi. Divided by 4 must be the current through that resistor, and thus the current going downwards. I notice here that all my resistances are the same, so I can multiply through all of my equations by 4 to cancel all of those out. I'm going to solve for V phi in this equation. I'm going to eliminate it in this equation here so that I have everything written just in terms of V so that I can solve that as my open circuit voltage. I've taken this top equation here, I've multiplied everything out, I've solved for V phi. Then I took this equation here and I simplified it. Now I'm going to plug in my V phis with this expression so that I can eliminate V phi and leave the only variable as V, the nodal voltage that gives me the open circuit voltage. Now I can cancel a V and a V. I can bring over the 60 and I end up with 240 equals 2V, or V is equal to 120 volts. And so if I've got 120 volts here, this is ground, then my open circuit voltage, VOC, in this case, is going to be 120 volts. And I found VOC. The next step is to redraw the circuit to find the short circuit current, ISC. We'll use pretty much the same circuit, except here we have a short circuit, a wire connecting terminals A and B, and we're measuring the short circuit current in this case. We see that with I1 flowing in, some of I1 will go to I3, some of that current will go as the I short circuit. So we can go ahead and write nodal equations again. We have a ground here, but since this is a short circuit, this is still 0 all the way up here. These currents, I1 and I3, are going to depend on V phi, though, and we don't know what V phi is, so we'll need another equation, which we'll pick from this node here. Now we'll write up equations representing each one of these nodal KCL equations. Now that I have these two equations representing these two KCL equations, I want to find the short circuit current. I don't know what V phi is, so I'll need to find V phi down here to simplify this. Down here, I can multiply through by 4 to cancel everything out. And if I simplify, I can find an expression for V phi, and now I can plug that in up here. This is going to be 120 when I plug in 20 for V phi. This is going to be 40. And so if I have 120 divided by 4, that's going to be 30 is equal to 40 divided by 4 is 10 plus ISC. So my short circuit current should be 20 amps. Beg your pardon, that should be a negative 10 volts, or 10 amps, and so that should be 40 amps, should be ISC in that case. So we found ISC, and lastly, we'll find the Thevenin equivalent resistance. In this case, we have a dependent source, so what we're going to have to do is we can still deactivate the independent sources, but we'll have to apply a test current and measure the test voltage produced by that dependent source to find the Thevenin equivalent resistance. So here's my circuit. I've deactivated the independent voltage sources. There used to be voltage there, so to deactivate it and make sure there's zero voltage by putting a wire. I like to leave the terminals to remind myself that there used to be voltage sources there that I replaced. I still have my dependent source, and I still have where that dependent source is measured from. But what I have to do here now is apply a test current, and I'm going to measure the test voltage that I have as a result. And I want to figure out what this test voltage is, and the ratio of these two is going to be the Thevenin equivalent resistance that I have over here. So if I'm looking for this test voltage, I'm really doing a nodal analysis again. This is already 0. If I can find the voltage V at this node here, then this is V, this is 0. That voltage there is my test voltage. I'm going to leave my ground where it is. This is 0, this is 0 all the way around. All of this is still 0 over here. The voltage here, if this is 0 and this is V phi, then this voltage here is V phi. If this is 0 right here because it's connected to ground, and this voltage is V phi, then I have V phi right here as well. And what I have in this case is my test current coming in, and I'm going to have some current flowing, let's say, this way, and this way, and this way, and that way. And so I'm going to, again, have to do some KCL equations to try to find out what V phi is in this case, and to relate that to my test voltage and my test current. So my test current flows in, and I've got I1 and I3, so my test current is going to break off to be those two values, and I can see that's going to depend on V phi, and so that's another variable I'm going to need to look right here. And what I've got is I3 is flowing in, and I've got I2 and I4 flowing out of that node. I'm going to go ahead and write my equations. I can go ahead and multiply through by 4, and I see right here that Vt is equal to 3 V phi, or that V phi is 1/3 of Vt. So I can take this and I can plug it into this other equation up here to eliminate the V phis, and I can find the relationship between the test current and the test voltage. If each one of these here is 1/3 of Vt, and this is 1/3 of Vt as well, then Vt minus 1/3 of Vt is 2/3 of a Vt left. So here I end up with Vt equals 1/3 Vt, and my Thevenin equivalent voltage is the test voltage divided by the test current, which comes out to be 3 ohms. And that 3 ohms is consistent with 120 volts divided by 40 amps as well, so we can check and make sure that we did everything correctly. So we have this complicated circuit connected to some load resistance R. We had to do some calculations, but we were able to find the open circuit voltage, the short circuit current, and the Thevenin equivalent resistance of the supply circuit. We did all of that because we wanted to find the value of R, that load resistance R, to allow maximum power transfer, and we know that happens if the load resistance equals the Thevenin equivalent resistance. So in this case, if the Thevenin equivalent resistance is 3 ohms, then the load resistance should also be 3 ohms in this case, to allow for maximum power transfer. If we want to find the actual maximum power transfer, the easiest way to do that is to actually connect that load to the Thevenin equivalent circuit. The Thevenin equivalent is equivalent to the other one, so we might as well use it. Our Thevenin equivalent circuit is this guy right here, where our Thevenin voltage is our open circuit voltage, our Thevenin equivalent resistance is what we found, and we picked the load resistance to be 3 so that these two match each other. If we want to know the power being delivered to this resistance, we need to know the voltage being delivered to the resistance, and we can use a voltage divider for that. We found that the load voltage is 60 volts. Using Ohm's law, we can see quickly that the current should be 20 amps flowing through that load resistance, and then the power being delivered to the load in this case is going to be the load voltage squared divided by the load resistance, in this case 60 volts squared divided by 3 ohms. Which is 120 watts. This 120 watts is the maximum power delivered to the resistance.